Okay, so good evening, everybody. Thanks for staying until now to also listen to this part. My name is Cesare Pautasso, and I come also from the University of Lugano. I did a PhD at ETH in Zurich in 2004, and I also did a number of years as a postdoctoral researcher in the same university. Then I spent some time in the IBM Zurich Research Lab, also in Switzerland, and then I moved to Lugano to become an assistant professor in 2007. I work in the area of software engineering in general, and in particular software architecture, business process management, service-oriented computing, web services, mashups, RESTful web services, and autonomic and cloud computing. So many different topics. I do not expect all of you to be familiar with all of them, but this presentation will be very different than the previous one. This is not about taking science and simulating it, turning science into an e-science. What we want to do here is look at artificial systems, software systems, large-scale, complex software systems, and figure out how do we actually design them. We are interested into modern software system where the elements are called services. That's why the title of the talk, service-oriented computing. And we are also interested into working with services that are stateful and they work well with the web, the World Wide Web. Also, that's the second part of the title, resource-oriented architectures. That's sort of a link to the web. So before we get into the detail of this short lecture, let me just mention what we do in our group. I have a group with 3 PhD students and 1 postdoc right now. One of them is working on design decision modeling for software architecture and design. The other one is working on service composition, in particular Web 2.0 mashups, and we will talk about some of these things today. And I also have the postdoc and another student working on self-organizing service-oriented architectures, where the concept of self-adaptation, adaptability plays an important role in conjunction with services. So these are some of the topics that we work on, and there is a lot of room to be filled in the middle with some interesting connection between them. But of course, I do not want to talk about these things in detail. I want to give you a little bit more of a foundation of what you should know if you want to be able to actually do some research in these areas. Now, some of this foundational material comes from the lecture that I do in software architecture and design. This is one of the main lectures within the Master of Software Design that we offer at USI, and it's it sits in the middle between the basic software engineering course and the software design and evolution class. So we try to do basically top-down design, and when you start from requirements, you have to do an architecture of a system. And here they do it bottom up, right? You start with an existing system and you have to change it, you have to evolve it. So to introduce the topic of services and architecture and so on, I just wanted to give you a little bit of a look back in the past of software, right? How software used to work, right? There was once upon a time, many years ago, software used to come in boxes. If you buy a computer, you want to install software, you have to go and buy a box, take it down from the shelf, open it, and you find, what do you find inside? CD-ROM, you're a young person. Used to be disks, floppy disk. So you have all these boxes in which the software used to come in. Nowadays, software runs in the clouds. Oh, sorry, there's a typo. Software runs in the clouds means that software is just there for us if we have a working internet connection. That's sort of an assumption. Nowadays, you buy a new computer, you don't have to spend days installing software on it. You just boot it, you assume that there is a browser in the computer, and then in a couple of minutes, you can already start to log in into your favorite web services and start working with the computer.
Choosy people are not satisfied with this level of software.
Yes, so that's just to contrast a little bit, right? Of course, The whole point is that there is native software, locally installed software, which can completely access what the hardware can do. And then you have this kind of service-oriented software, which is remote, has the power of the cloud, but is also sort of, there is a much smaller channel, which is what the web browser can do. Yeah? So in other words,
to be really comfortable, one needs locally installed client application with the rich UI.
Yes, yes. So in that sense, it's the same. If you think about how technology has evolved, you have this thing called Google Maps. Yeah, it's a very nice web application. You can have the map, you can zoom, and you can do a lot of things. But there is another very interesting application that is called Google Earth. Yeah, it's a native 3D and it has powerful graphics, and there is always this race. Yeah, you have native capabilities; they are platform dependent. Whereas you have these web-based things that are platform-independent, or they are basically browser-based. Yeah? So what happened in this sense is sort of changing the way we deliver software. Right? It's now delivered as a service. And so there was a long time ago, when people, the web came in the early 90s, and people were asking themselves, oh, what is this thing? What is a website? Yeah, I hear about this thing that you can navigate and you can find information. And then some time passed, you have this exponential growth, and then people asked, okay, so nice to meet you, what is your website? Yeah? You are a company and you're nobody if you do not have a website. Yeah? People will not be able to, if you want to look up somebody, if they don't have a website, they don't exist. And the same thing happened instead of the web, which was mainly something for sharing documents for human consumption. Yeah, you have a person navigating with the browser and figuring out where to go. We switch from that is human-oriented to something that is oriented for machines, for programs, yeah, for making programs interoperate. That's why they're called services. And that basically was the same trend, right? In the early days, it was you have this system. Why should this system has a web service interface? Why should it has a web API? Yeah, everybody was in doubt. There was a lot of hot, hyped technology growing around that time. But nowadays, you expect every system to have a web API. You expect every system to be connected or to be connectable. Yeah? That you can write some software, and sort of by default, this software should be something that you can link on the web. Yeah? And then there are many different ways to do it. Yeah? There is the REST way to do it, or there is the SOAP way to do it, and they sort of conflict against each other.
Are there any considerations how we bound the segment of applications to apply this to? As there are very many subject field applications which still do not need any web API. So definitely there's the applications like what you are saying about are numerous. There are very many of them. But how do we define this area?
Well, basically any application that you want to be able to reuse, yeah, that you want to be able to integrate with other applications. Yeah? You want to, if you are trying to build or you're trying to design an open system, yeah, then this fits. And if you say I have a closed system, it's a local system, it's a non-distributed, and maybe it's an embedded system that doesn't have to communicate with any other system, then this doesn't apply. But the argument is that most software systems nowadays are open, so they have the potential to talk to any other software system that runs out there. And this is more and more affecting not only pure software systems, traditional business applications and so on, but also embedded systems. Nowadays, a car, it's a software with 4 wheels. Yeah, you have possibility to connect a car to the internet. This has a lot of implications in privacy and all. Both ways, yes. And then you have all these security issues, right? What if some hacker takes over the car while you're driving? Yes. But this is sort of a new mindset that you have when you write software. Right now, software is something that is open and is meant to be used as a service. That's what I want to talk about today. So to introduce this topic, and please let me know once you want to stop, yeah, because this is a subject of a 1 semester lecture. So I can do this in 30 minutes. But in principle, to talk about this topic, I want to break it down into 4 steps. Software architecture, because there is this concept of architectures, and probably we can try to do it this evening. And then at some point around 8:45 or 9, I don't want to keep you here too long. You've been already for quite a while. And then we can continue tomorrow with the other parts on the discussion on what is a service, what is a software component, what is this, is there something new with services? And then why do we need services in the first place, right? We have these open systems, we need to be able to connect them together, so what kind of technologies are available to connect different systems, and then the final goal is to show you that the web, or the REST architectural styles that stands behind the web, can also be used as an effective mean to actually connect different systems together. So that's a little bit the overview about what I want to present. Let's see if we can actually do it in this limited amount of time. So to try to also keep answering your question and explain why this is important, right? So typically in school, in the university, you learn about these topics. Databases, software engineering, programming languages, and those make an assumption. They say, you want to learn how to program, well, you start from a blank screen and you write your code. It's a new program. Every time it's something new. It's a database, you have an empty database, you fill it up. In reality, nowadays, we have been writing programs for 60 years. So the software out there has been written. There is a lot of it. And so it's important that instead of building things from scratch, we also learn how do we take these existing systems, open them up, and reuse them and interconnect them in new and different ways. So when you go to a company, typically they tell you, yeah, we already wrote the software, now you have to maintain it, now you have to integrate it, now you have to connect it with others. So
you have to rewrite it.
yeah, in some cases they say, oh, the software is rotten and you have to throw it away and rewrite it. But in other cases, you will be able to achieve new functionality by simply taking these as more or less black boxes and glue them together somehow. So this is what about services are really meant for, is integration of existing softwares. And then you end up in these kind of situations. You have these application landscape, you have these enterprise architectures, where you have millions of lines of code structured in different subsystems connected together with different kind of technologies, and you need to keep track of them. You need to be able to say, what if we go here and remove this box, because we want to throw it away. Is something else going to be affected? So to actually build such a system, you have to be able to go and take 2 of those systems and draw a line between them. Seems to be a very simple exercise that you go and say, well, we have a system and we have another one, and then they are connected together. It looks very easy to do on the whiteboard. But once these systems, maybe they're running different parts of the world, and they have the open internet in the middle, and you have all kinds of problems that you need to solve to do it. That gets actually quite interesting and quite complicated. So in reality, what we want to achieve basically is the idea that we have all these systems. Sometimes they're called silos. They're called vertical applications. They have some kind of user interface, and then there is a person that sits in front of the 2 systems, has something in his mind that says, oh yeah, this is what I want to achieve, and he starts to, for example, reads from one system and types into the other. Then you have achieved integration by hand, but that's what typically people do when they are in these kind of situations, right? They have many applications, many data sources, many systems, and they look at them and they say, oh yeah, something happened over here, I have to update something else over there. And if you put a person at the center of the integration, it becomes very expensive. People make mistakes, and if you do this once to do a very ad hoc kind of integration, this is okay. But if you want to repeat it over and over again, the goal is to actually get rid of the person and make this automatic. So that you can actually draw an architecture like this, where you say, these are all my systems, and then I have the bus. Yeah, I have this enterprise service bus. I have this connector. I have this technology that allows us to transfer information reliably and securely between all the different places and build something out of the composition of things. So to give you an example of what this is one particular kind of service composition. It's called a mashup because it gives you the illusion that you have a single application. But in reality, behind this single application, there is lots of separate pieces. In this case, lots of different databases. Yeah? So this is an application for searching for houses. Yeah? You want to rent up an apartment or buy a house. You go to this site, and they give you an integrated view over all the databases for offerings for houses in Switzerland. And they also improve it so that not only do you get the list, which is already very convenient because you don't have to go to 10 different places. You go to one place. But they also show you a map. So they can take some of these things, put them on the map, and so you see which one of these houses are closer to where you work and which ones are in the bad parts of town and so on. Yeah? So this is a mashup because at the UI level, it's a single application, but behind it, you have a lot of different components. Yeah? So to build this kind of systems, what people do is to design specific composition languages, yeah? Specific programming languages to compose systems. Yeah? Once you switch from writing a program that is made by very small statements, like you call a function, you do simple arithmetics, you write some algorithm, and this is some code that runs locally. You can switch and say, well, every step of this program is going to be an invocation of an entire system, an entire remote application that runs somewhere else. So basically, when you are in this situation, you want to reuse software, you want to reuse components, then you can build applications like this, right? Each one of these boxes is a system, an entire system, and then you can make the data flow between the different systems and specify everything using a visual notation. This is the tool that we have developed at the University of Lugano, right? You build a library of services, you can drag them, you connect them, and the whole system runs. And it generates this kind of mashup interface. So that was sort of to introduce service-oriented computing. Now I want to get a little bit more in detail and talk a little bit about software architecture, which is sort of the assumption or the background for all this kind of work. Yeah? So when we talk about software architecture, well, before we talk about software architecture, let's just talk about architecture. This is just a metaphor. Yeah? There's also software engineering, right? There is something called engineering. It has a very long tradition, very established methods, yeah, to model, predict, and change the world. The same thing happens with architecture. Yeah? We can design, study the art of building, right? We make these beautiful buildings. Look at the nice room where we are. An architect has designed this. And software people, they look at architects and they say, yeah, we are also designing things, but at the end we don't have a building, we have a software system. And the properties of architecture should also be shared by software. Yeah? What are these properties? Well, when I design a nice building, this building should be built and last for thousands of years. Yeah? There are some examples of such things, simple constructions built by sticking stones on top of each other, nothing else, and these structures have been standing for literally 2,000 more years. Yeah? There was this aqueduct, we have water flowing there, and this is a structure built by the Romans just with stones. Yeah? And this in Latin means very strong, robust, stable, yeah? Something that you construct and it will not fall down. Yeah, if you build a building, you open it up, the people go in there, and then it crashes. That's not what you want to do. Yeah? At the same time, buildings should be also beautiful. Yeah, you should also do a design that has some aesthetics. Yeah, you should have some taste in your choice. Yeah? This is very obvious to see with buildings. Yeah? You look at it and say, I want to run away from this building, or I actually want to go inside. With software, yeah, can you actually say that the software is beautiful, elegant, simple? And of course, that's the most important property, right? Something should be useful. Yeah? You should do a building that has a purpose. Yeah? You should build a bridge that links two different sides of a valley. You should always satisfy the customer. Yeah. When you build a software system, you should build a software system because people are paying you for that. Yeah. So don't forget that. Now, in terms of architecture, what does it mean to do software architecture? Well, we don't have it's just a metaphor. Yeah? What we're interested basically is the large-scale properties of a system. We're not interested in algorithms or data structures. Yeah? This is fine-grained. This is very small kinds of decision. We are interested to study the global properties of a system. We are interested to study the design decisions that affect the whole life cycle of a system. So it makes sense to work with the software architecture of a system when the system becomes large and complex enough. Yeah? So in this sense, how large? Yeah? How do we measure the complexity of a system? Well, in that sense, it should be a software system that has a lot of functionality, a lot of parts, a lot of moving parts, a lot of components. And these components, it's not enough to have a lot of them, but where the real complexity comes from is between the interdependencies. This is, if you remember the discussion on the computational science complexity, yeah, you have an algorithm that is squared. It doesn't make sense that you have it's not enough that you have a computer that is 1 billion times before, right? It still takes you, 100,000 years to compute it. So here the complexity square come from the connectivity, yeah? It's not, you add one more component, you have n potential connections with all the others. Yeah? Also, complexity comes from a high rate of change. You have built a software system and people keep asking you, please update, please make it do something else. Requirements will always change faster than you can keep up with them. Also, architecture is fundamental for systems where you have a high investment, yeah? You have a high replacement cost. Yeah? You said before, can I just throw it away and rewrite it? Yeah? People have been trying to do that. But these are $1 million projects. You write the system, you maintain it for 20 years. Can you just throw it away and replace it? Maybe you don't even have the interface specification anymore, right? The system itself becomes its own specification. That becomes really, really difficult to replace. And if this is a mission critical system, well, it means that the system must be in operation. Otherwise, your whole company or your whole organization that depends on it will not be able to function. So you cannot just say, well, now we go on vacation for 1 year, and then we have all the software people reprogram the system, we come back and work again. This simply doesn't work. Also, high complexity systems typically rely on heterogeneous technologies, which basically means that your life as a developer of this system becomes complicated because the system has been in operation for such a long time that it has seen all the various kinds of technologies that are there. Yeah? So this heterogeneity is also a very difficult thing that makes this complicated. Yeah? If these two are two software components that are running on the same operating system, written with the same language, very, very homogeneous, writing a connection between them becomes easy. But if these are heterogeneous, built with completely different technologies, how can we actually think about connecting them together? Yeah. That's a little bit one of the challenges that we have with composition. So, yeah. Is that okay if I continue for 5-10 minutes? Because now it was the time that we were supposed to stop, so I hope. You have to go? Okay, bye-bye. So, software architecture is a metaphor. One very good metaphor that comes from the real architecture in software is the concept of architectural styles. Yeah? So this idea that you design something and you don't design it as an ad hoc solution. Yeah? You just don't do it from scratch as a completely new thing. You actually fit your solution within the constraints of a style. Yeah? If you look at this picture, does it remind you of certain style? What style? Do you know? It's a Gothic style. Yeah? You look at it, if you know what the Gothic architectural style, it's very easy to recognize it. So the style is important in architecture. Oh, and this one, what is it? It's Florence. Do you know also the style of this? It was, also the historical time when this was done. Renaissance, yes. So that was also, a particular time in history when the architecture was done like that. Styles are also related to the area, the geography, or the time. And sometimes the style begins in one place and then it moves in different places. Gothic started in one place in Europe and then it spread everywhere. Also Renaissance. So the point is that when we have something that has a very large size and complexity, like I was talking before, then it's very difficult to capture the exact architecture. Yeah. Think about the World Wide Web. The World Wide Web is a system that has 1 billion parts. Yeah. There are web browsers everywhere, there are web servers everywhere. They are all connected and talking to each other. But we cannot say, stop the web right now and take a snapshot. Yeah. This is too large. It's too fast. What we can do, however, is understand the style. Yeah? So we can understand basically the basic context in which the solution is applicable, what are the constraints that are going to guide you as a designer to actually do it in a certain way, and what is the quality that you expect out of the resulting system. Yeah? So this is basically something that comes from architecture, right? We need to design a building that has a certain quality. We do it with constraints. Yeah? There can be constraints on the technology, there can be constraints on the fashion, there can be all kinds of constraints, and then some styles will be applicable to do certain kinds of buildings. Yeah? For example, if you want to do a church, you are in Russia, then this is what you get. Or anyway, at a certain time in the history then people used to do it like this, but it doesn't. You know, you can take this and try to apply it to do a train station, yeah? But maybe the context is not the same. Yeah? So then maybe you don't want to do it this way for some reason. Yeah? So in software, there is a very simple style that everybody should know about. That is basically the layered style. Yeah? The layered style is a very simple constraint. Yeah? The constraint is that you split the system in layers. And why are they called layers? Do you know? Well, in software, there is a layered style. Layered is like that, right? You have, it's like a cake. Yeah, you have a lot of things. And so, what is the constraint that you have when you do the system in layers?
Each layer abstract details from the outlets.
Mm-hmm. Yeah, it's a way to abstract.
Actually,
Each thing can interact only with the table layers.
Yes, yes. So that's a very important constraint. Right? As a designer, you say, I will build a system and I will organize it in abstraction layers. And the constraint is that if I'm here, I only see the one above and below, but I don't see here. Yeah? So effectively, layers will hide what is below. That's why it's called abstraction. So once you do that, what is the quality that you get?
well, actually, the lowest in the entire file. The lowest quality, well, not always, can be. It is
But
some composition of the qualities at the layers.
yes, that is correct. So of course, at the end, the quality of the whole system is sort of the sum, or a function over the quality of the parts.
Some tricky composition.
Yeah.
On the particular layers.
Yes, but quality can be also seen as, for example, the performance of the system, or the scalability of the system, or the capacity of the system to change, to evolve.
You can hide something on the upper layer. You can hide something that is on the kernel.
So, for example, if I change something over here, yeah, which layer is going to be affected?
It depends. In the worst case, all of them. In the worst case, all of them would be affected.
Okay.
In the good case, only the
neighbor.
Only this one.
Yeah. So in the good case, if I do the right kind of change, right, then the change only propagates here, and these guys will not notice. Right? So that's a good quality, good property. Yeah.
In the good design.
Yes.
In the well-designed system, yes.
Yes, and in other kinds of changes are very difficult to localize within a layer, right? These are typical interface changes, right? You say, oh, now I have the data, I have the logic, I have the display, and I add a new attribute into the data. I have to process it in the logic, and I have to display it. So this is a cross-cutting layer, a cross-cutting change that for which the layering was not a good solution in that sense. Yeah? So there are some changes which remain isolated and others will actually evolve. So when it comes to layering, I want to give you some examples of typical layers that have been introduced, also in the context of services. Yeah, so we can connect it to what we were talking before. So one classical example is, of course, OS, application, and hardware. Yeah, these are different layers. Yeah. You can run an application, it depends on the OS, and the OS, well, sometimes it depends on the hardware as well, but these are typical things that do not mix. Yeah, the application is separate from all these things. You can have one OS for many applications. Now, if we make it fast forward it to this time and age where everything is cloud-based, then these layers are renamed as something like platform as a service, software as a service, or infrastructure as a service. Yeah? IaaS, PaaS, and SaaS. Yeah, nowadays, everything is as a service. Yeah? So that's sort of to show you that the word service is actually coming up quite often in this context. Yeah? Even though this is sort of called cloud computing. Yeah? Have you heard about these things? Like, okay. So another example, which is a little bit older, is this state logic display pattern, which is a sort of a refinement of the layered style, which says, now I have 3 layers in the system. One of them is going to be the UI presentation. The other one is going to be the application layer. And what is the third? Yeah, so the database, the resource manager, separated from these things. Yeah? And again, the reason for splitting the system like this is to make sure that you can keep evolving the system over long periods of time. Yeah? So in this case, once you design an application, the data is the most precious part. Yeah? A user will invest time to give you the data, and you should never lose it, so you should properly manage it using a database. This is the part that changes the most often. Yeah? You used to do desktop applications. Now everybody wants to have a mobile application. Yeah? The rest of the system is the same. Yeah? But you change the technology that you use to deliver the system to the user and present it. Yeah? Now, once you cut the system like this, also you build a system that by default, automatically, it comes with a service API. Yeah? Because the split, the separation, the cut between the client and the presentation, the way that you interact with the system, the UI, and the server, it's exactly what is defined as being the service API of the system. Yeah? There is also here other standards that are used, like for example, web widgets, but that's not so important. This is the concept here. Right? Now, when it comes to SOA, it's also a complex style, service-oriented architectures, which also includes this concept of layers. Yeah? So we'll not get into too much details, but also here we have a sort of a layers of encapsulation and reuse. Yeah? So when it comes to services, you can see they sit in this, conceptually, inside this central layer. Below them, you have the systems that we want to reuse and encapsulate. So we have services that will use software components that already exist, and they are legacy. Yeah? And then once you have the services, you can reuse and compose them, mesh them up together using business processes, these specific ways to program how to compose a system, and portals which sort of give you, again, the client, the UI of the system. Yeah. Okay, so that was the introduction that I want to give. I think it's already a little bit late. What I want to continue to talk to you about tomorrow, I think we will start at 11. Yeah? 11:15? Yes?
It's the announced time.
Yeah, it's good. So we will have a lecture by Professor Sharigina, and then when she's done, I will continue with the next part, and we will talk about different technologies that are available to build these kind of systems. So because we originally announced this, it will finish sort of now, so I don't want to, because of course I can talk for another 2 hours, but I think it's been a long session, a long afternoon. Do you have any questions about this part? Have you seen some service-related topics in your studies? Architecture? Sorry?
In practical.
In practical, right. But not from academia, so not from academia.
The course is CAAAS by Berkeley. Everyone can take it, but it's not on design.
Okay.
The course based on Ruby.
Aha.
Kind of simple, so it's oriented architecture.
Yeah. It is. But it's more for programming in Ruby, some kind of Ruby on Rails, this kind of framework and so on. Yeah. Yes, yes. Yeah, that is really sitting. It's a very thin layer that you put here, but the whole concept of SOA is much more deep and complicated than that. Yes. Yeah. Okay, so thanks a lot for listening. I hope to see many of you tomorrow again. I know it's a Sunday, but that's the kind of schedule that we set up. Thanks.